Welcome you all in a lecture series of probability, random variables and random process. As we have seen that signals used in communication system are basically of two types. First is the deterministic signal that is completely specified as a function of time and can be represented mathematically. For example, cosine function. And its expression is AC cos 2 pi fct plus phi c. Here parameters such as amplitude AC, frequency Fc and phase phi c are known completely. And another is called non-deterministic or random signals. These type of random signals cannot be represented mathematically. Also, the future values of these signals cannot be predicted in advance very precisely, as the random signals cannot be represented mathematically, hence called non-deterministic signals. For example, speech, video signals, computer data, sensor signals, etc. These types of random signals may distort or interfere the transmitted signal, that is in the form of electromagnetic waves. So the random signals which interfere the transmitted EM signal in the communication channel called noise signal, and these noise signals are additive in nature. So at the receiver side, the antenna receives a noisy signal, that is a combination of transmitted signal and noise signal. Now, as the random signals cannot be determined mathematically in a precise manner, so it can be described in terms of statistical or average properties, which includes a probability theory. So in order to understand the noisy performance of the receiver, we have a thorough knowledge of probability theory, which includes the concept of random variables and random process. Next, we say that in the communication system, when the noise is introduced with the information, then the combined signal becomes a random signal. And in order to analyze and measure these type of random signals, a mathematical tool is used which having a statistical and average property, and which can further be used for our signal detection techniques. Before proceed further, we discuss some points regarding probability theory based on statistical experiments. First is, for any random experiment which cannot be determined mathematically, their outcomes are called random events and random signals. Second point is, the outcome or random events are based on statistical properties that is obtained using operation called expectation, and it includes a function of random variables. Third point is Gaussian random variables. For the analysis of random signals, Gaussian random variables play an important role. These random variables are used for obtaining the noise performance in communication system, which we will discuss briefly in our upcoming video lectures. Next, fourth point is white noise. For the analysis of communication system that is based on noise performance, a white noise is used, which is basically a additive white Gaussian noise. And at last, in the communication system, noise is treated as a narrowband noise, which can be easily represented in terms of in-phase and quadrature components, hence called narrowband communication signal. Now, before discussing random variables and random process, we go through the concept of probability theory. In probability theory, we mainly focus on 3 points. First is called experiments. So, what is an experiment? Experiment is a set of rules that control the operation or experiment which is to be performed. And when the experiment is performed one time, then it is called a trial. Now, after a trial, we get some results which cannot be predicted very precisely, and these results is called outcome of an experiment. So we can say that within an experiment there are number of trials, and corresponding to these trials there comes a number of outcomes. And after combining all such outcomes for every trial, we called it event. So in probability theory, for any experiment, we get some outcome, and the combination of outcomes for every trial, we called it event of that experiment. And this whole process, that is experiment, outcome and event, is called random experiment or random process, because here the outcome of every trial is not predicted very precisely, hence called random process. Also, outcome may differ because of random phenomena. For example, in a case of tossing a coin, here in this experiment the outcome may be a head A or a tail B. Here the outcome cannot predict very precisely. Now let tossing a coin n times, which means there are n number of trials, and corresponding to these n outcomes, we select a combination of events that is called a desired possible outcome of occurring head A. So the event A called desired outcome of head occur any times out of total n number of trials. From this observation, we define a relative frequency of occurrence of head A, and it is equal to the ratio of Na upon n. Here, Na is the number of times head A observed, and capital N is the total number of trials for the experiment of tossing a coin. This ratio, that is Na upon n, is called relative frequency of occurrence of event A, and it is a non-negative real number. Now, if we assume that event A, that is head, occur in all the n number of trials, so in this case Na is equals to n, and the relative frequency ratio for a head A is equals to 1. Similarly, if we assume event A, that is head, occur none of the total n number of trials, so that Na equals to 0 and the ratio Na upon n become 0. And this conclude that the relative frequency of occurrence of head A is greater or equals to 0 but less than or equals to 1. Now we note a point. When the total number of n trials are very small, then the computation of relative frequency is not possible and the result become uncertain. So in order to determine precise relative frequency, the experiment must be repeated very large number of times, which means n tends to infinity. So limit n tends to infinity, Na upon n is nothing but a probability of event A, that is head, and the ratio Na upon n is simply called a relative frequency of occurrence of head A. Now, after discussing the concept of relative frequency to determine the probability, we move to the axioms of probability. Axioms means rules or principles. So first, in every experiment, each possible outcome must be associated with a point, and this point is called sample point, and it is denoted by small s. And the collection of all the sets of sample points called sample space, and it is denoted by capital S. So here both sample point and sample space is called an events. Small s corresponding to elementary event, that is occur only one time and associated by a single point in the sample space, while the capital S is called a sure event, which includes all the possible outcomes of the experiment that surely occur. Or we can say that sure events are the combination of number of elementary events. Beside elementary and sure event, there is an impossible event that is represented by null set phi. Now, to understand the concept of events, we take an example of throwing a dice. When we throw a dice, we may get 6 possible outcomes. That is 1, 2, 3, 4, 5, 6. Which means corresponding to these 6 possible outcomes, we assign a sample points. So in the experiment of throwing a dice, there are possible 6 sample points. Also, we can arrange these 6 sample points in one-dimensional space, that is along a straight line in increasing order. So the combination of all sample points constitute a one-dimensional sample space denoted by capital S. Next, in the concept of events, we mainly focus on the event statement. For example, when we say an event of a 6 show, this corresponding to event of sample point only 6, and this is an elementary event. Also, when we say even number of dot shows, then in this case we take a combination of even samples, that is 2, 4 and 6, and it is called subset from total 6 sample points. So in second example, probability system consists basically of 3 points, that is 2, 4 and 6. Now using all the concepts of event statement and according to axioms of probability, we make a summary of related points. So first point is, the sample space consists of all the possible outcomes, which is basically a combination of all the elementary events. Second is, here we take an example of throwing a dice. So the class of all the elementary events are the subset of sample space capital S, which includes all the possible outcomes, that is 1, 2, 3, 4, 5 and 6. Now, when we say a class of even number of dots, then we have only 2, 4 and 6 sample points, which are even number of dots. And the third point is, the probability of each event A in a class E is noted by a probability of A, and this having a following properties. First is, probability of sample space, that is a sure event, is always equals to 1. For example, for sure events, that is had A occur in all the trials, n equals to n. So in this case, probability of A, that is limit n tends to infinity, na upon n is equals to 1. Also, the probability of A, that is event had A, is a non-negative number, that is less than or equals to unity. Or we can say relative frequency of occurrence A, that is na upon n with limit n tends to infinity, is always greater than or equals to 0 but less than or equals to 1. So both the properties of probability of A have a relative frequency interpretation. Next, we take an example of tossing a coin, including head A and tail B as outcomes, and both are mutually exclusive events. In this experiment, events of class E is A union B. That is the probability of A union B equal to probability of A plus probability of B. Here, probability of A means probability of event head A and probability of B means probability of event tail B. This can be understood in terms of total n number of trials. So let us consider event head A occur in NA trials and event of tail B occur in NB trials. Then we can say A union B occur in NA plus NB number of trials, because here head A and tail B can never occur on the single trial. Therefore, the total trials, that is N A plus B equals to NA plus NB, which is equals to N A union B. Now divide both sides by total number of trials, that is N. Therefore, expression becomes N A union B upon N equals to NA upon N plus NB upon N. As this random experiment repeats for large number of trials as N tends to infinity, So the probability of A union B is simply equals to probability of A plus probability of B.